This is the Amp Hour Podcast. Released July 25th, 2023. Episode 640. Software-defined power supplies with Werner Johansson. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Werner Johansson from Koitech.
Hey Werner, how are you?
I'm doing well. How are you?
I have brought up your talk multiple times. I'll get to the point here in a second, but I brought up your talk multiple times, and I keep thinking every time I bring up something that I remember you talking about, I keep going to the Amp Hour and like searching Werner and seeing like, wait, he hasn't been on the show yet. It's actually, you had given a talk at Hardware Developer Didactic Galactic, the meetup I used to do in San Francisco.
Yeah.
And I bring up that talk multiple times on the show, and I'm really glad you're here now so that I can bring up this show instead of just that talk.
Yeah, it's been a continuing thing of mine that designing power supplies apparently has become something I do a lot, and I like them to be software defined.
Yes. So that is the talk that you gave at HDDG all those years ago. And I remember I think it was a pretty simple microcontroller you were talking about that was actually doing the power supply control in software.
I've been using the Atmel Now Microchip X Mega line for a lot of that.
That's what it was, yep.
Because of its ADC, because it was in a class of its own, a 2 mega sample SAR ADC.
Oh, wow, yeah. That's basically an ADC with a micro attached, right?
So unfortunately, all of those are successive approximation, but that's what you get in that price. But it's a 12-bit really fast ADC for a microcontroller, so you get a fairly short lag between the actual sample, and then you make a regulation decision, and then you have a DAC on the output or PWM.
Yeah, nice.
So that's where I started.
Got it. Yeah, and so since that time, so that was San Francisco. Since that time, you have started working at Koitech, and what is Koitech?
So Koitech is a spin-off from the old Sony Mobile, the cell phone company that very few people heard of these days. We were internally, because I have an 11-year-old history at Sony Ericsson and then Sony Mobile, both in Sweden and in the US. We were looking into power save and measure the actual power consumption of the cell phones. And there were some tools available, and they were all missing one or two other features that we wanted. I started looking into that because we were using this when I was doing Linux mainlining, trying to do automation. So we really didn't care about the high accuracy current measurements. We just wanted to see that, okay, does it draw 300 milliamps? Or does it draw 20? But we also wanted to have serial port control and some keyboard emulations. We could press certain keys to enter service mode, DFU mode, that kind of things, reflash automatically. So I did that project, and that's the CDB Assist, which is also from this time frame, right around the talk, which must have been 2016, right? Yeah, it's something like that.
That sounds right. Yeah, I can pull that up to double check, but make sure it's still on the internet too. That's the other thing, you know. These things disappear sometimes.
So that's an open source thing that's actually not, well, it was initially based on Xmega, and then I did a version based on the Cypress, now Infineon PSOC 5LP, which is a really interesting piece of microcontroller / programmable logic.
Oh yeah, yep.
Okay. And analog programmable stuff.
Yeah, it's got like the switchable, you can switch in like op amps, like nothing. I remember the profile on those is like none of the parts were great, but you had a lot of them and you could make them configurable, which is like super awesome.
So it's like a CPLD, not an FPGA, but a CPLD and then some programmable switch cap filters and a reasonable 24-bit Delta Sigma ADC actually. Not super great, but it wasn't bad. But it's an insanely expensive microcontroller.
Yeah, and there was a Bluetooth version as well that was even more, right? Or is that when they went to 6?
That's the problem, that they actually lost more or less everything that was reprogrammable in that. They significantly shrunk all that great
Oh,
stuff that the PSOC 3 and 5 had. But the PSOC 6 is the one with the dual core and the Bluetooth, and then there's the PSOC 4 that's basically just a Cortex M0 with Bluetooth. That's nothing really special. Now the PSOCs were interesting.
I see. Okay.
We're actually still using that in production fixtures because it has an insane amount of analog I/O, and it can drive an external CPLD for muxing, because it comes in a 100-pin package, so it has a lot of I/O. But that was the initial thing, and it got me started into the whole programmable digital hardware as well, the CPLD stuff.
Right. So I think my first exposure to the Koitech stuff, I think you had sent me. You and I met each other at the San Francisco thing, and we kept in touch.
The old one.
I think you had sent me the actual unit. I actually have one of the ARCs. Yeah, the ARC. Yeah. So you had sent me one of those, and I tried that out, and that was 2019, maybe. So maybe describe what the box looks like. People might recognize it when they hear the description.
Yep. So it's aluminum extrusion, black anodized, and it's basically one large heatsink because of the electronic load capabilities inside. So it's a functional design. Even though I like the design, it's an engineering design. So it's a small box with a USB port and a DC jack on the back, banana plugs, and an expansion connector on the front. That's basically it. It's a completely headless multi-instrument.
Yeah. Yep. And that one was basically a pass-through style, right? So basically, I needed to power that externally. Is that correct, or maybe I'm misremembering?
No, it's well, you need power available, but there is a power supply inside.
Or is it self-powered?
It's a 2-quadrant power supply, so it will source positive voltage, and it will sink negative current. So basically, if you have a positive voltage on the outside, you can sink that into a negative voltage into the electronic load. So that's what it does. And so it has a DC jack, or if you're only going to power small things like coin cell based devices, you don't need any other power supply than the actual USB port. So that one goes. It will deliver 500 millivolts to 5 volts, depending on how it's been configured. Due to the old design that one has, it's a design that started way back in 2000, late 15 or 16. So if you're USB powered in maximum accuracy mode, you can output up to 3.75 volts because of all the burden voltage drops inside. Because we only have 5 volts, there are no step-up DC-DC.
Right. Yeah, makes sense. And it's not USB-C, so you couldn't use the PD and get higher voltages to step down later, right?
Unfortunately, not at the time. It's something that was designed for single cell lithium ion, basically. We're back to cell phones. That's where it started. And that's what we had in most things, except the tablets in certain cases. So it's up to 5 volts. And unfortunately, due to us not having a negative enough voltage, the common mode voltage on the instrumentation amplifiers doesn't allow us to go lower than 500 millivolts on the output.
Yep, that makes sense. Yep. I have to ask, were you dismayed by the Keithley 2306? Was that your previous thing that you had been using on cell phone stuff? I know that was on a lot of cell phone stands.
we use that a lot, actually, for initial bring up of charging circuitry, etc. But it's a less than ideal instrument to try to automate. I know that it has GPIB, but it's still a mess to actually try to get the.
I don't know, man. There's a 2x16 LCD display on the front. What else could you need? And a couple of arrows.
then you try to explain that to the normal software developer that has to deal with this, and then it's just question marks. It's just blank stare. So, and the whole thing about compliance voltages and all. It's a very, very complicated thing to explain to somebody that does not have the slightest of interest in learning all about an SMU. So this is half an SMU basically, but
I know.
with a lot
Yep.
easier
Yeah.
user interface because all you do is you interact with the PC software.
Mm. Yep. Cool. Yeah, that's great. And I mean, I came from Keithley, and I was kind of indoctrinated into like, no, you need a front panel, no, you need to have buttons and interactive, whatever. But I am 100% in the headless these days. I mean, like I'm Analog Discovery 3, Analog Discovery 2 and 3, and like Koitech and Jewel Scope and all these things. Like it's just first off, I think portability. Second off, scripting.
Right.
Third off, I don't know, like just size on my bench. I don't have room for these huge half rack boxes anymore. Even if I did have room, it's not a great use of space. I'm sure Dave, if he was listening, would be shaking his head. But I just for me and my current lifestyle of IoT devices, headless is the way to go.
So basically, the whole thing is I have the same thing that I don't have infinite amount of space. And ergonomics wise, if you have a lot of instruments mounted on shelves, several stacks high, you need to get to it as well, which is not great. If all you have is a large-ish screen and the keyboard and mouse or some other input method, it's a lot more convenient. So I'm thinking, no, I'm not 100% headless because I have some Keysight DMM and a large electronic load and a signal generator, but I don't really use the front panel, but it's there. It's all Ethernet connected, so it's all remote controlled anyway. Because we're using the high-end Keysight
Yeah,
DMMs to do calibration
right.
of the Koitech stuff in the factory as well.
Yeah, and I think that's the other thing too. Is once you have the tooling in place, it's like it's just a different mode of operating, and I think it's kind of bench side versus computer side, right?
Yeah, and then how often are you actually at your desk doing testing? I mean, we had people doing lots and lots of field testing in cars, I mean, IoT devices. They tend to move around, at least some classes of it. So you actually need to do measurements on the go.
Oh yeah, okay.
So that's one way of doing it. I mean,
Yeah, right, right.
it's easy enough to
Yep.
just throw in your bag the
Mm-hmm.
Koitech instruments in that case. If you have a reasonable USB port with the new version, the 80As, you get up to 15 watts in most laptops these days. Unfortunately, not more, but that's what you're getting 5 volts, 3 amps.
Yeah.
It's still pretty good. We're using some of it, and there is some conversion losses,
Yep.
but you can power some
Which is still, I mean, pretty good.
most battery powered equipment, I would say, but not all.
Yeah.
So there is still DC adapter available because the new version of this box can output
Mm-hmm.
a lot more power if it has power available either through USB-C or the DC jack, because it actually has a proper PD modem, so you can negotiate up to 20 volts, 3
Mm,
amps. But
mm-hmm.
no computer will
Yeah.
give you that yet. No hub will give you that.
Oh wow. Okay. What will you have to have like a dongle plugged in the wall or something, or a wall jack?
Basically, what I had to do is that I had to splice together the CC pins and V-bus and ground from a USB PD adapter, and then ground and USB data pins going to the PC. 2 to 1 USB C adapter. I got inspired by the Google Twinkie PD analyzer that I found, but I couldn't source. So I had to build my own of, yeah, when is that? A month ago, basically.
What's it called? A USB Twinkie? I've never heard of that.
It's a USB PD analyzer so
Yeah.
that you can
Right.
actually analyze the communication over the control channel on the USB C link. So you have the two CC pins, CC1 and 2.
Mm,
Either you connect resistors to, so you get the voltage. So that gives you a rough idea. Are you a host? Are you a device? Basically, source or sink.
who's in charge here?
Who's in charge? And then you can start doing the modem thing and actually do communication and then decide, no, I want to switch roles. I want to switch to a different contract. Actually getting the source and the sink to decide on the best contract to use. So it will say I can output 20 volts, 3 amps. I can output 15, 9, and 5.
It'd be useful in the field. I'm just staring at my laptop as we talk about this stuff. So I have a USB C charger, And those things, yeah, the chargers are actually beefy. They can do 100 watts. But what if there was like an inline before the computer, right? So I go USB charger at 100 watts into like some interstitial, and then from the interstitial that negotiates the 100 watts there. Some of that goes out to my Koitech, and some of that goes to the computer. Is that possible, you think?
Yes, and it's definitely possible. And I've been very, very close,
Oh yeah.
more than once, to design a hub like that.
Okay. I think it would be useful for a lot of things. I mean, like I'm just powering so many things off USB C these days too. Like I mentioned, I have an Analog Discovery 3. I have other USB C stuff kind of all running there, and just having that power available. It's almost like we'd have to to kind of like hijack the high power.
Yeah, the main thing is that you need a very beefy USB power supply to begin with if you're going to do that and actually have some. I mean, the USB PD EPR, the extended power range, now that can go up to 48 volts, 5 amps. So you get 240 watts out of a USB C port.
Whoa, really? Wow.
That's the latest stuff. It requires specific
Uh-huh.
cables, which are electronically
Uh-huh.
marked, which is the fancy way of saying that yes, there is at least one microcontroller that can be reprogrammed in the cable.
Uh-huh.
I mean, it's insane when you think about it, how cheap and small those things have been, so that you can just shove one
Yeah.
or two in the cable and then get
Yep.
it
Yep.
hijacked and get malware stored into it somewhere.
Well, that's a different problem. Yeah.
It's a
Yeah.
different problem. It's just that I have the background from
Right,
security,
right.
so you always think about
Yeah.
that.
Yeah.
Unfortunately,
See, episode, I don't even remember what it was. MG from the OMG cable. Have you seen that thing? Oh boy, that it's creepy. I mean, like Mike's awesome, but like that device, and just the fact that I think about this every time I plug in a cable these days. Of just like you think about these USB jacks that are at airports, and these charge boxes, and just
yes,
what are you
yes,
plugging into? Just like people should always be asking this stuff, and I still don't
yeah.
do it enough.
It's trust no one. That's
Trust no
you
one. Yeah,
just
yeah.
you don't. So this is the problem, where previously with a USB A, a regular USB 2.0 USB A cable, it's
uh,
4 pins plus a shield. So
yeah.
you have the ground and the
Right.
D bus and D
Exactly.
plus and D minus. There is nothing else. So if you isolate D plus and D minus, you're good because there is power. It's 5 volts always. On USB C,
Yeah.
it's a
Right.
lot more complicated because you actually need the USB C CC pins for communication. An ideal source will give you 0 volts on VBus until it actually detected that there is a device connected on CC. The 5K1 pull down on one of the CC pins indicates that there is a device connected. And if you provide that, then the source will start communicating over that line. It will actually superimpose digital communication like modem on top of that. So there is really, it's a lot more difficult to isolate yourself completely because the computer, the Apple MacBook I use, it has the new 140 watt power adapter. So it actually uses the 28 volt 5 amps setting. So it talks a lot. It's an insane amount of chatter on the CC pin before you actually get to 28 volts.
Yeah. Yeah.
And it identifies the serial number of the charger, it identifies the serial number of the cable. There is a lot of things that you can buffer overflow, I'm fairly sure.
Uh, wow.
So it's just one of the other attack vectors, and it's good because USB-C is the ubiquitous adapter of choice, and it's starting to get really useful when you can get up to 240 watts. But going back to the whole hub thing that you would need, it's perfectly possible to do something like that, but you end up with a power brick for that, like the docking stations. I have a Dell docking station with a 240 watt power supply, I think. It's a fairly hefty power supply.
And that's not USB though, you're saying?
That's no, it's one of those barrel plug, the really
Yeah, right.
large laptop
Yeah.
style things.
Some of it I do wonder about, like just the amount of copper, just current going over these copper connections. You get some buildup on these things over time. It's like, the size USB C is a interesting thing, and there are multiple pins that are dedicated to power, but they're not big. There's not a ton of copper there.
There is not a ton of copper, and I mean that's the reason why they topped out at 5 amps.
Uh-huh.
But 5 amps is a substantial amount of current, and now when they've gone to 48 volts,
Yeah.
the tip of those contacts have a very, very specific shape, so that you can direct
Oh.
where the arc will go,
Huh.
because there will be an arc when you
Huh.
unplug at full load. If you're not, you want the CC pins to disconnect first, and then you want
Uh-huh.
the voltage to drop
Yeah.
very, very quickly when you unplug under full load, because otherwise you're getting a sustained arc because it's DC. This is
Uh-huh.
the problem
Yeah.
with 48 volt DC systems, that when you
Right.
get an arc, it's a very large arc.
Mm.
So it's an interesting problem, and that's why most of the USB-C pinned the USB-C connectors that you find, they're still only rated for 20 volts.
Yeah. Yeah. That's why we should switch back to DB25 for everything, and then you can just put a couple of those pins. Put the 48 volts on the left side, you put the ground on the far right side, and you're good.
They were also not designed for
Not
hot plugging.
not ideal. I know. Can you imagine though? Like that, it feels like someone just the anti Apple method. Just like what, screw
Yes.
it, we're going back to DB25.
Oh, it's going to be interesting to see what Apple comes out with when it comes to cell phones, because they're still holding out with the whole Lightning
Yeah.
connector on the
Yep.
phones, but they
Yep.
moved to USB-C most everywhere else.
So I'd love to get back to that idea of software-defined power supplies that you talked about in that HDDG talk, which of course I'll be linking in.
Right. More power supplies in
More power supplies. Yeah.
in more ways than one. So it's a thing that keeps coming back, doing everything from the world's first wireless tattoo machine, for instance, also using that same power supply.
Mhm.
That's was featured in that talk. It's been remodeled in a new version as well.
Oh, cool.
What we have been using is Koitech, Arc, and now ACE programmable power supplies, electronic load, and precision current measurement. We actually started that way back in 2011
Mm.
as a side project, where we started experimenting with battery powered rotary tattoo machines.
Cool.
And you had some really interesting design requirements, that it could only weigh half of the cable,
Oh, wow.
because that's a cable that normally hangs off of your tattoo machine and then into the floor, down into the floor. That's the weight that the cable adds when you're holding it. So 64 grams, if I remember correctly, was the total amount of weight for the battery and the electronics. So it's radio controlled over 802.15.4, not Zigbee, but the same radio.
Uh-huh.
So that's the first place where this power supply actually got used. The idea of having a completely software-defined buck boost regulator,
Huh.
because the other solution we had from Linear was an IC with an H bridge in it,
Yeah.
and we kept destroying that when we stopped the motor because of the back EMK.
Yeah, because the back EMF. Yeah. Yeah. Right.
It completely killed that chip. It didn't survive. So we needed bigger MOSFETs.
Huh.
And the smallest way to build this was with the Atmel, now Microchip X Mega microcontroller, because it had the fast 2 megasample ADC, so we could actually do constant current, constant voltage regulation in firmware.
That is super cool. And actually, this came up again. I was thinking about this when Cian Lore was on the show recently, and he was talking about this new CH32V003, the little 10-cent microcontroller from a
Right.
RISC-V microcontroller. And he was building his own buck converter out of it. And I was like, I actually knew someone who did that with a different part, obviously. And it kind of had me calling back to this HDDG talk back in the day.
Yeah. For the normal control loops, it's actually easier to get it stable than trying to make it analog.
Why is that?
Because of the phase relationship is basically you only need to know what's the latency from me sending a new command to the DAC or to the PWM until you actually see the change back into your ADC conversion, which is very, very easy to measure. And then it's very, very easy just to add that delay You don't need to switch out components. You don't need to do any of that because you tune it
Yeah.
completely digitally.
What about the external? Like one of the things with control systems, though, is that you have external capacitance or just delay in the system because you're powering something out in the world. So how do you deal with that then?
Yeah. Then you can have a dynamic delay if you encounter this. So you can have a longer delay if you encounter that it takes too long for this change to show up on the output.
Uh huh.
I've been doing this for LED lighting control as well, where you drive a system into constant current. And this is always a problem when you're in constant current and you lose regulation
Uh huh.
because you disconnect the LEDs. They tend to shoot that up to maximum voltage possible.
Right. Yeah.
So you need to detect that as well and immediately cut the power and then do a slow start when you detect that you actually have something connected to it.
Hmm.
So all of that is way easier to do in a digital control loop than the analogs.
So do you keep like a local variable of like last known delay? Is that kind of like how you deal with that?
I have been doing it. Most of the time, we haven't had the need to actually tune it because it's been stable enough. For the Koitech stuff, it's now these days, it's actually a hybrid of an analog control loop and a digital one.
Hmm.
So it's an interesting thing because it is difficult to get short circuit protection working reliably when you have a digital control loop because you can't react fast enough because the AGC has a certain amount of latency before you even get to seeing the numbers and you can make a decision out of it.
Hmm.
So you need basically a two-step process. You have an analog cutoff when you know that there is a short circuit or severe overload, and then you can react in firmware to take control of that and make a nicer regulation when it comes to constant current, for instance.
Hmm.
So it's best of both worlds in that case because in some cases you don't want your current sensing burden voltage to be seen on the output of the power supply.
Right.
So then you actually have your sense, your analog remote sense on the output of the power supply, which means that you need a fairly fast, potentially unstable regulation to make sure that you have the correct voltage on the output. And then you can slow that down digitally.
Got it. Yeah. Okay. So you have to. Sounds like you have to really kind of maintain the state of your control or what's it called your phase state space or something like that.
Basically, your phase margin, if you
Margin.
look at
Yeah.
it from the
Yeah.
mathematical point of view. The main reason why there is both analog and digital control in some cases is the fact that there is no ADC converter and front end with that low latency. I mean, the X Mega was the fastest one I could find, and it took, I think it was one clock cycle per bit plus an additional one. So it took 13 clock cycles at up to 2 megahertz.
Hmm.
That was the latency. And then every clock cycle, you got a new sample, but it was 13 cycles delayed.
Right. Yeah, like a pipeline almost, huh?
Yes. So it was
Yeah.
that's why that ADC was so fast because it was pipelined.
Hmm.
No other MCU that I found at that time in that small of a form factor had a pipelined ADC, which could also do differential measurements actually, which is kind of interesting.
Yeah.
It had some
Yeah.
other quirks, but it's a really good ADC for the time, and I still see it being used.
Everything in this space is interesting to me because it's like I guess the other one that I think about, obviously a very different kind of problem space, is like real time audio processing type stuff where you're pipelining stuff, you're taking a reading, you're trying to get something back out around the loop so that
Yeah,
people hear it. So like digital guitar pedals and things like that. You can't just like delay it forever and sit on the data and process it because the people want to hear it. They're like expecting some kind of real time. They're used to the analog side of things,
yeah, exactly.
but there's also that same delay problem.
I was involved in another project with real-time audio actually. When is that? 2 years ago now. The Elk Audio guys has a product where you can play together with your band and practice over the internet.
Oh yeah, yeah, that was huge during the pandemic, right?
Yeah, exactly. This came out on the tail end of the pandemic due to component shortages and whatnot. They have a bridge with an IMX8 Linux system with a real-time processing on the side and an FPGA, and then dealing with the local audio codec and ADAT support in the FPGA, and then just sending that in as TDM into the IMX audio system. So
Huh.
they have a very, very low local latency. So basically, you just add the internet latency on top of it. So you can do real time jamming sessions from Stockholm down into Italy, which is
That's pretty cool.
hundreds and hundreds of miles.
Yeah. How do you deal with the delay then? Because like it's like that. There's also like the brain processing, right? So like I want to have a reactive kind of like I hear that my drummer is doing something, and I want to react to that, quote unquote real time, human real time, right?
Here's the thing that
Yeah.
if you're used to playing on a stage, you need to take speed of sound into account.
Yeah. Right. Right.
So you have those milliseconds of latency to play with.
Mm-hmm.
It's a few tens of milliseconds. That's all you have.
Mm.
Then you're gonna start to lose your sense of this. It no longer makes sense.
Mm.
I would say that you have around 30 milliseconds or so, and it also depends on how fast you play.
True. Right. Yeah. Dream's different than like someone playing a ballad, right?
Exactly.
Yeah.
So it's a very, very interesting space
Yeah.
when it comes to audio processing that needs to happen fast, and you
Yeah.
need to have it pipeline, but you can't delay it forever. It needs to
Right.
be done,
Right.
and you need to be able to set it out.
Yeah.
We have the exact same problem in the Koitech Ace, the new hardware, because interestingly enough, the IMX8 M Nano has the Cortex M7.
Which is a beast on its own, by the way.
It's a very, very useful real time system. That's
Yeah.
exactly the core that we're using in the Koitech Ace, the
Okay.
RT 1060 series.
Yeah. Yeah. That's great. Which is the same as the Teensy as well. We were just talking about that in the last show that was just released.
Yes, and it's due to Mr. PJRC himself, Paul.
Uh huh.
When I was in discussion with him during the last Maker Faire in Bay Area in
Uh huh.
2019, that it is the 1060 that actually sits in the Ace and not the 1050 that I was initially looking at.
Ah, interesting. Interesting.
He strongly discouraged me from selecting the 1050 series.
Paul, if you're listening, he's not listening, but he's on my list of guests that I refer to as white whales because I've tried to get him on the show multiple times and he still refuses. But I'm gonna keep trying.
Oh,
Yeah.
no, he's great. I mean,
Yeah.
so
He's great.
that was a very, very good decision looking at the errata that you could see for the 1050 when you looked into it. So
Yeah.
back
Yeah.
in 2019, it was a very, very short list of Cortex M7s to choose from. There was a SAM something from Microchip slash Atmel, which had like 20 pages of errata.
Oh my god.
And there was the NXP part, the 1060 series, and then there was an ST Micro where you couldn't get Ethernet and high-speed USB in the same silicon for some odd reason. I was looking into that. We wanted to have the possibility to have an Ethernet port and high-speed USB. So there was just two of them left. One of them was the SAM with a huge errata, and then the 1060 series from NXP.
Huh. Yeah.
So that's how I ended up with the 1050, and then talking to Paul, and then it's a 1060.
Got it.
So that's the one that's on the Teensy 4,
That's
I
right.
believe.
Yeah. 4 and the 4.1. Yeah.
Yeah.
Yep.
We're using the slightly larger footprint, though, because
Because you don't need to be teensy.
our board is fairly large. You don't want to manufacture that as a high DPI
Yeah. Right.
board
Yeah.
if you can avoid it.
Yeah. Well, let's talk a little bit more about. So the Ace is the Ace is the new one. Could you explain what the Koitech kind of problem space is solving?
Yeah. What we're trying to solve is people wanting to make their battery-powered IoT devices last longer. So you want to optimize your hardware, you want to optimize your firmware. And traditionally, optimizing firmware has been kind of difficult because you need to involve somebody that can do high accuracy power measurements, and then you need to do that together with somebody that actually knows how the firmware works. It would be ideal if the firmware developer could actually do this themselves. A regular instrument to do this will be too complicated to figure out for software developers. You want a UI that is more software developer friendly, basically. So we're trying to make it as easy as possible to do power, energy, current measurements together with GPIO and serial port input, so you can trace what you're doing and record that together with the analog measurements, so you can actually get it synced. So if you have a trace output from your firmware, you can immediately see what's happening during certain parts of the current consumption. So that's the super simple problem space we're trying to solve. And what it actually is that it's a programmable power supply, which is 2-quadrant. So we can source positive voltage and we can sync the negative voltage, the negative current coming back. So that means that we can discharge a battery, creating a battery profile, and then you can emulate that battery back because we have programmable output impedance or resistance on the output so that it behaves like a battery. Again, coming back to the whole software-defined power supply, it's very much completely up to the firmware / gateware to do that. So that's a great part.
Yeah, and so the one we're talking about as well, the ACE is the successor to the ARC. Is that right?
Yep.
Yeah.
So basically the same concept applies. It's just that the voltages and in some cases the currents have changed. The initial ARC that's been out since 2017 has an output voltage of 500 millivolts to 5 volts at the highest range, with a maximum output current of 5 amps. It can sync up to minus 2.5 amps. The new ACE is 0 to 25 volts output, and it is plus minus 5 amps.
Yes, and so now I can blow up devices with abandon.
So here's the thing that we had that scenario in mind. So the software will actually have a preference setting of the highest available output voltage, so that people don't make that mistake.
Yep, good.
Most people don't want 25 volts on the output.
Right, you got to click a couple buttons to get there, I hope.
At least need to go into the preferences and set, I want more than 5.5 volts. So you need to select your maximum voltage.
I know that this is going to mess some stuff up.
Yeah, I mean, 25 volts is a lot.
Yeah.
And the interesting thing is that we've gotten some questions that, okay, but I'm powering it from my 5-volt USB. Yeah, it doesn't really matter because there is an isolated power supply inside that will generate plus minus 30 volts.
Yeah, it'll get there.
At all times.
It's just current limited, not voltage limited, right?
I mean, it's a fairly simple construction, but with some quirks, because it has 3 isolation domains. I mean, the interface, the USB and the DC jack on the back is chassis ground referenced.
Yep.
And then you have the main terminals, the banana plugs on the front. Those are isolated. And then you have the expansion port, which contains the serial port, all of that, and additional sense inputs. That's also isolated from both chassis and the mains.
Interesting.
So 3 completely separate isolation domains.
Yeah. Why did you make the expansion port separate? I would expect that to be on the same ground as the output.
So there is a reason for that, and the reason is when you design battery-powered devices and you have a column counter or just current shunt, it's much easier to put that shunt in the negative terminal on the battery, because then it's ground referred.
Right.
Then you don't do high side current sensing.
Yep. Exactly. Yep.
Which also means when we are replacing the battery, our minus terminal is no longer system ground.
Right. Got it.
So that's why it needs to be separated.
Uh-huh.
In the ARC, the original ARC, there is no isolation. And we actually had this problem a couple of times because you accidentally short out your column counter on your device. Basically, it believes it draws no current at all.
Right.
That's the result of it, which also means that it's difficult to charge a chargeable battery if you're using that shunt to control current.
Yeah. Yeah.
So, and that's the simplest reason why you can actually connect several of these ACEs in series if you want to generate even higher than 25 volts of current as well.
Oh, stack them up, huh? Yeah. That's pretty cool.
Up to 200 volts difference is what it's rated for.
Wow. And that's limited based on the isolation of the transformer internally?
Isolation of the transformer, capacitors, decoupling capacitors from ground plane to ground plane, and just general sanity check that most of these instruments will not let you lift ground off system ground more than 1 or 200 volts. I mean, looking at the general DMMs from Keysight or any of the other known brands, they also have very, very specific markings that your minus terminal can be a maximum of 1 or 200 or 250 volts from ground.
Yeah. And if you don't know what Werner's talking about right now, this is not a feature for you.
Exactly.
Yeah, when you start floating grounds, and then you're like, I think I should measure something on my laptop, which is chassis grounded, or my desktop computer is like, oh, you're gonna have a bad day real fast.
Yeah, I mean it's
light up your day.
Complicated.
Yeah.
I mean unfortunately that's how the first design was done, because it was the easiest to get going. And looking back, doing type approval of a device that has 2 isolation domains, it's very difficult to not have some interesting harmonics show up on your cables, which have very little ground return.
Yeah, right, exactly. Yeah, that current wants to get back somehow, but it's not the traditional path.
It will find a really annoying way back to system ground. And it tends to show up on emission measurements, especially when you're also doing simultaneous sampling. So that's another feature, that we increase the sample rate a lot from our 4 and 1 kilosample a second in ARC to 250 kilosample a second on the ACE. And it's simultaneous sampling ADC. So we have 8 ADCs. Well, it's 2 4-channel AD converters doing simultaneous 250 kilosample conversion.
And do you do like the step offset thing where each one is just like a sample or 2 behind the other?
No, there are actually 0 samples behind.
Oh, interesting. Okay.
There are 4 identical sigma delta modulators and filters in those chips.
So why do you do it all at the same time then? Was there a benefit for that?
Because you want to make sure that voltage being measured and the current are from the same time. Otherwise, you can't properly calculate power.
Okay.
Those samples need to be from exactly the same time.
Okay.
So it's calculating the power on a sample basis, and then you average it out for energy consumption over time.
Got it.
So this all gets mangled from the 2 ADCs into 2 FPGAs, which turns it into audio signals for the IMX RT1060. So I can use the great serial audio interfaces on the IMX to retrieve all these 32-bit samples.
Yeah. Okay. Interesting. And there's additional software, or sorry, there's additional silicon on those parts that is beneficial that it's an audio versus just kind of like a raw data format.
Yeah, because otherwise you have to basically do SPI, or some parallel access if you're gonna just capture data. But then you need to be constantly talking to that peripheral, saying, I want to transfer all this data. It's a lot easier for the audio hardware to recognize the frame marker, to know which word is which. So which is the first word of this multi-channel audio stream, and then just DMA that straight into their own separate buffers in internal memory.
Interesting. And so then are there 8 DMAs going into 8 sections of memory as well?
It's only 3 separate DMAs which does that. It's due to the fact that it's 3 separate interfaces. On this RT1060, you don't have an 8-channel audio interface. And on the other side, because of the isolation between the main side and the expansion side, there's 4 channels coming from one ADC on one isolation domain. There's 4 others coming from the other isolation domain. So it's 4 plus 4. And they're sample locked to the same oscillator. And this comes back to emissions. There is one single reference driving every single thing in this design. And it cannot be spread spectrum because it's the sigma delta modulators. They really dislike frequency variations because it creates noise.
Yeah.
It needs to be a very, very sharp spike, which is very bad for emissions.
And you send that across an isolation barrier as well?
Yes.
Huh. Using an opto or something else?
It's one of those really small isolation gap transformer RF thingies.
Okay.
OnSemi has a few of those, and TI has a few of those.
Yeah, I was going to say TI does those too. Yeah, okay. So like basically like the digital isolators.
It's digital isolators.
You're saying a pulse over a digital isolator, and do you have to characterize the delay in that as well then? Or is it you just assume it's the same across because you're using the same isolator?
They are specified to be isolated to isolator within a few nanoseconds.
Oh, okay.
There is a very tight spec on those. These are the high frequency ones, which are 100 to 150 megabits per second.
Yeah, those are expensive.
Yeah, they're not the cheap ones, and they're also one of those that were slightly unobtainium during chip shortage. That and the ADCs.
Yeah, the problem there is that all the car people like those too.
Yeah,
they like the high speed across barriers.
Yeah. The good thing is that they tend to use the slightly slower ones, but we had problems with car people and the RT1060 series because we're using the larger pitch, the 0.8 millimeter pitch BGA, because we didn't want to do a high density board on a board that's 140 by 100 millimeters. So it's a standard. It's one of the things that our favorite prototyping PCB places can do without even flinching. It's just
exactly. Yeah, they're like, oh, just that? Oh, no problem, right?
Exactly. It's one of those.
Yeah.
So if you keep to 0.8 instead of 0.65, no, it's not 4. It's a lot more sane than that. It's slightly smaller. It's the one that's on the TNC4. I think it's 0.65. I can't remember. It was a bit more difficult when you needed some specific pins, because this has been carefully chosen so that I'm getting access to all of the audio subsystem pins.
Yep, totally.
And it required some very particular pin muxing in this. It's still 196 balls, and it still was difficult to actually get all of that out together with USB and Ethernet and 2 SPI buses and an I2C bus. So there's quite a bit of interfacing going on, because you do housekeeping with the ADCs over SPI, and you also bootstrap the FPGAs over SPI. So there is one SPI bus going to each isolation domain, so you can do that in parallel, and then you have all the audio interfaces of data coming back.
Yeah. Huh.
So it's an interesting setup. It's basically a very large audio interface.
Huh. It's really interesting. Yeah, it's an interesting idea. I like how you did that.
It's one of those. Yeah.
Yeah. One thing that came up. So you had actually sent me one of the ARCs way back in the day, and I've had that on my bench for a long time and doing measurements and stuff. And then I got to hang out with you and Vanya, your CEO, and some of the other teammates at Embedded World this past year
Right.
And I got to see a demo of the new functions, which are actually something I had not seen on any of the other products, because this is a popular space. I feel like, especially like my doing IoT stuff, I feel like the high dynamic range, super low current, all the way up to like transmit power type of stuff. There's a lot of stuff out there, including, the low, medium, and high end solutions that are out there, but I had not seen the battery stuff. Can you explain that?
Yeah. So basically, because we have the ability to do current syncing, we can connect a battery and then perform a discharge cycle at varying levels of current, measuring the voltage when we have put this load on, and basically recreating the internal resistance of the battery at each state of charge. This has been done by Keithley, as you're very familiar with,
Yep.
many years
Yeah.
ago. They tend to have fewer steps. Typically, it's one step per percent, because that's what you can possibly manage with the small, relatively small display, simple keyboard, if you're not doing remote management of it. So
Yeah.
that's the still expensive test equipment that we were using and the battery guys were using at Sony when this was initially conceived, because we needed to do power measurements, power optimizations closer to the firmware guys, and they just couldn't figure out the whole thing about battery simulators, battery emulators. With a lot of these settings, just to get it to sync current, you need to make sure that you have the compliance voltage set up correctly. Otherwise, output voltage might go negative. It's a very, very different world when you're entering proper SMUs.
Yeah. Right. Yep.
And it's difficult to explain to people that's not really interested in battery technology. But you need the technology to be able to measure the impact of firmware, because looking at it, firmware has a huge impact on battery life. If you missed out to turn off peripherals, you forgot to go to sleep. I mean,
Yeah.
all these super, super simple things that it's going to be very difficult to have a discussion between the expert of power measurements and the people doing firmware.
Yep. One thing that really popped out to me is that you showed me on screen, you have this characterization. So you stick a battery on this thing, say just a generic. So I go and buy a generic lithium ion pack from somewhere in China, which I've done before. And they tell me it's 850 milliamp hours, whatever. And you could actually characterize it, not only the capacity, but like the actual curve all the way down. You could start to average them and you would show me a curve basically, right?
Yep, you start at the fully charged battery.
Yep.
Either it's a rechargeable one or it's a primary cell. The same procedure is applicable to both. You will discharge a battery until you reach a certain cutoff voltage, and stop the profiling and say, I'm done. I got this much capacity out of it. Basically, the amount of charge you were able to extract from it. So that would be coulombs or amp hours, or energy as in watt hours.
Right. But then the key thing for me was not just that, because it seems like there's a lot of things that, you could do that with like a DMM, two DMMs and a timer, right? The key thing for me is that then now you have this curve that you showed me on screen and you're like, oh, you could replay it. That's the thing that I don't think I've seen that before. Maybe it exists other places, but I had never seen that before personally.
We've actually had it for quite a few years on the Arc as well. The same concept applies. It's just that it's now more accurate because we have better control of output voltage. But yeah, it's you. As soon as you're done with this profile, you can immediately go and select that the mode should be battery emulation and select this profile, and then you select where you want to start.
Right.
At which state of charge you want to start. Do you want to start at the full battery? Do you want to start at 50% depleted or close to empty?
Right.
And then you can choose whether it should track discharged, which a normal battery would do, or you can just say, no, I want to stay right here and freeze so that it's not going to discharge or charge.
Or you could do an accelerated timeline too. I'm assuming, right? You could say do 100, 75, 50, 25, 0, and then you could see all of the different things of how your device might. I just imagine, like, I remember seeing this and thinking, like continuous integration testing is like a great target for this sort of thing.
Continuous integration testing of things like how does your device deal with battery is about to go empty.
Exactly. Yep.
And
Exactly.
you want to replay the exact same scenario every time. You want to start at 90% depleted and actually see that the device performs a graceful power off, whatever
right.
it's supposed to do.
Right. Right.
So yeah, it's exactly that. And for firmware development as well, when you're actually developing these things, you might actually want to have the battery freeze at a certain percentage.
Mm-hmm.
It's a very interesting thing, which is a super simple thing when you're looking at it as a feature, but the gains is actually huge because you can do this yourself if you're fast enough with a regular power supply, but it's not going to be as good because you need to be able to react fairly quickly to changes in load, because that's what happens when the battery either it gets depleted or it gets old. Because the more charging cycles you put on a lithium ion battery, the higher the internal resistance will become, or the impedance. So that's what killing the battery earlier and earlier, typically for devices when the battery ages, because you can't deal with this drop in voltage when you have a huge spike. When your radio turns on, for instance, it just collapses.
Right. Exactly. Yep. Yeah. It's like a brownout during a transmit. Right.
Yeah, exactly. That's what's happening because the internal resistance is nowhere near zero, even though the lithium ion batteries are way better than coin cells.
Yeah.
I mean, coin cells, you measure it in tens of ohms,
Yeah.
which is why you can't just shove random transmitters on a coin cell because it just doesn't work.
Right.
Some of them, like LoRa, you can actually do on coin cell, but
maybe have a bunch of caps there too.
yeah, and
switch it over to a super cap circuit or something like that and manage that.
Yeah, the problem with supercaps is that they tend to leak a lot.
Yeah.
There's a lot of leakage current.
Yep.
But there are some interesting battery types with low internal resistance and high cycle use, which you can actually use. So it's very dependent on which battery you choose. The whole cycling thing is something that is new and unique to the ACE, actually. So we can now do automated testing, charging and discharging the battery in cycling as part of the advanced battery validation stuff.
Oh, okay. So you would actually, you discharge the battery, then use the power supply internally, recharge it, and then you kind of see it degrade over time.
Yeah.
Oh, cool.
It's a very, very simple way of doing it. So basically, think of it as an arbitrary waveform generator, basically, which is capable of setting a positive or negative current going in and out of the battery.
Oh, you would do that. It wouldn't just be a constant current. You would actually.
Now you can pulse it.
You would pulse it.
So you can actually the interesting thing is that you can categorize the battery even during charging by selecting two different or several different current levels during charging, and you will get the same measurement of internal resistance there.
Huh. Yeah, it is an interesting way to kind of think about it too, because like my own migration of how I've thought about batteries over my career. You know, it was always voltage at first, and it's like current, but really thinking about resistance, internal, really impedance, I suppose, of the battery is the best way to think about it because of how, and really like during delivery of power back out.
And there is a simpler and a very much more complicated model of that impedance. It's a complex impedance when you start to really drill down into it. It's very complicated. Certain battery chemistries have a slow start, for instance, that you basically don't get any energy the first time when you start to discharge it, and then it recovers. Coin cells are like that when they've been sitting around for a year or so. You actually have a passivation layer on it that you need to burn off for it to actually generate current.
So like if you manufacture and you stick it on a shelf somewhere, you kind of have to have like a startup mode sort of thing.
Basically, if you're doing the non-careful way of pulling it out of the package so that it actually touch both sides of it,
Uh-huh.
that discharge is typically high enough to trigger it. But if you're careful not to touch it and you haven't actually measured the voltage, it might take a while for it to engage.
Wake up so much.
Yeah.
Yeah.
So this is why you have this the 10 mega ohm input resistance of a multimeter. People tend to think that that's a lot, but 10 mega ohms at 3 volts, that's 300 nanoamps.
Right. Right.
So it's a sizable amount of current in this area, and it depends on what you mean by low power.
Right.
It means drastically different things to different people. When you're talking to automotive, it's low power seems to be milliamps. Whereas low power when you're talking coin cell stuff, it's sub microamp. I mean, it's several hundred nanoamps. That's low power.
Yeah.
That's basically our limit today with microcontrollers and sleep. I know that I had the Atmel X Mega thing sleeping at 250 nanoamps, but that was without any way except either a GPIO trigger or a reset to wake it back up.
Yeah.
RTC added another 250, so it was like 500 nanoamps.
Yeah, it's still not bad though.
It's still not bad.
Impressive.
I mean, but it's different people have different ideas.
Right.
I saw that Dave did the teardown of Keysight battery emulator the other day.
Oh, I didn't see that.
That's a low power version, according to them. It's less than 200 watts.
Yeah, I mean, when you're used to building things for the bench, it's a little different, I suppose.
It is. So I thought it was funny that, okay, it's low power, but it can deliver 200 watts.
Yeah.
So yeah, it's in comparison with their other stuff which is larger.
Yeah.
So it's I'm not surprised, but you can clearly see that it's not only low power when you see bus bars, really really thick bus bars inside. Then you know there's a lot of power.
Yeah.
We've made the design on a single PCB so that we actually don't need any connecting bus bars or wires inside.
Yeah, from a manufacturing standpoint, that's always the best.
I mean, from a manufacturing standpoint, when you're not making tens of thousands in each batch, it's way easier if you can have a single board. We can test that single board. We can calibrate that single board in one fixture.
Yep.
And then you perform final testing and get the labels and everything printed.
Yeah, I just think too of anytime there's cabling or someone tightening a screw down or any kind of manual assembly, it's just the cost, and complexity too, right? And other things that can go wrong. I don't know. Like I come from the space of boxes that were multiple boards and cables all over the place because you needed, for some reason, the users needed to have a front and back control on everything. So that means cables, and yeah, it really does complicate things.
The main thing with the traditional way of building in the DMM form factor, like the Keithless as well, is that you have a front panel with a circuit board behind that entire front panel. Mm-hmm. And then you need to get that into a base board that sits in the bottom of the box, and they tend to be fairly deep. So they're large boards. They're really large boards, and that as well.
Yep.
So when you try to make something for the desktop, we wanted it to be fanless, so that you don't have any annoying fans, and therefore it's designed like a heatsink, a functional design. So that's why we're limited to around 15 watts of dissipation on the electronic load. So you can't discharge at high power continuously. It's just not designed for that.
Where do you see the ACE and I guess the ARC in the old days? Where are these being used mostly?
They're being used for field testing. They're being used in production. They're being used for automated testing. And we have this in-house example of where we're using the devices to manufacture the new devices.
Ah, yes. The 3D printer style, huh?
Which is a good test of dog fooding. I mean, you're testing that your scripting stuff works. So it's in the loop, but in order not to introduce generational degrade, there is a NIST traceable calibrated multimeter in series, so that we're using that to calibrate the units. But everything is controlled by the expansion port and the main terminals of an ACE in the ACE fixture, and with an ARC in the ARC fixture.
Cool. Yeah, it is. The generational degrade is kind of the Xerox effect. Is that kind of the thing there?
Yeah. So you cannot trust. I mean, when you're 10 generations out, you can be you can be way off. That's just not how you can't do it that way.
NIST traceable is important.
It is. I mean,
at the end of it, there's a fluke calibrator somewhere. I know that. You go far enough back in the chain, and there's a 1980s fluke calibrator that some metrology engineer will not let you have unless you pry it from their cold dead fingers.
Yeah, it's interesting that for many years the Keysight, or it was probably even named Agilent, the 8.5
8753. Yeah.
Yes, it was unavailable in the EU because it wasn't ROHS compliant.
Yeah.
So it took them years, and I actually saw the dark version at Embedded World. They had one of those on display in the Keysight booth. So now it's back, and it's equally expensive.
You know what you had to do is you just got to sneak an 8753 under your shirt when you go through customs. Anything to declare?
Yes.
Whoa, did I have a big meal on the flight?
Nope.
It was very square. Very, very square. Yeah.
It's very
Why am I
square.
feeling 1U today?
That's a big multimeter. Those are, I mean, it has some significant limitations on what you can actually measure, but it measures very, very well. It's not something that you want to shove 10 amps through. I mean, that's not what it does.
But 10 nanoamps, sure.
So it's, I like the Agilent Keysight SMUs. Those are in the picoamp current with guard terminals and all that. That's slightly, I mean, that's not where we're trying to go. We're not trying to categorize silicon, for instance. I mean, that's when you need those 2-channel SMUs with picoamp of resolution. I mean, we still have a very, very high dynamic range on both ARC and ACE. We're measuring single-digit nanoamps up to 5 amps. So it's at least 1 billion to 1.
Yeah.
I mean, the step size on the ACE is 400 and something picoamps per step.
Yeah.
In that ADC.
I always caution people. I'm like, if you think you need, picoamps, just go check the price of the thing that measures it first. I mean, I guess maybe not the ARC or the ACE, rather. But square your monetary expectations towards your measurement needs and right size yourself. You should always right size your measurement needs.
I mean, it's more or less no. For electronics design, you don't need it. For semiconductor design, yes, maybe. So that's it's in that ballpark. So it's very important, and we've had this discussion before when it comes to sample rate, that we're replacing the battery on your device, and what's the first thing you typically encounter on the PCB? There is a bulk cap,
dumping current right into that,
which will inherently. Yeah, you drop it right into that, and you've automatically created a really nice low-pass filter. So we're sampling at 250 kilosamples a second. We're actually only presenting 50 kilosamples a second at the moment as the maximum number of samples that you can see. So they're all averaged out 5 by 5. Because most of the time, you don't even need that. Measuring sleep currents, you want even less. I mean, you want hundreds of samples a second, or even 1 per second, just to measure a sleep current. And when something happens, that's when you want the full battery.
The high speed mode, you go hyper measure at that point, right?
Yes.
Yeah, turbo mode. Yeah, hit
turbo
the turbo
mode, the turbo button. Basically, that's what you're after, because it creates quite a bit of data if you're gonna do this for a month or so. So you're limited by hard drive space only in this case. And if you're recording both voltage and current, and you can record an additional subsystem measurement as well using the expansion port. There is an additional ADC plus and minus pin which you can connect a shunt over, and then you can measure voltage on ADC plus to ground for your voltage measurement, and then current is the voltage across ADC plus and minus. And then you tell the software which shunt resistor you have, and then you're getting that current in amps as well. Great. So there's a secondary channel for that.
Well, Werner, I would love to hear more about this in the future. Where can people check out the Koitech OT Arc, or an ACE rather?
So you can check it out at koitech.com. It's Koitech.com, and it's available on DigiKey and the usual distributors for immediate dispatch.
You can get one tomorrow morning if you need.
Which is great.
Yeah, that's awesome. That's awesome. All right, well, Werner, thanks so much for joining me, and we'll chat soon.
Thanks for having me.